All right, let's see. So the whole idea is if I switch the x and y and I solve for y, I'm going to undo everything that was being done. Then what is the inverse function supposed to do compared to the original function? What's the inverse function supposed to do compared to the original? If the original function...
Rotate it?
Sort of. I'm with you. But more computationally, less graphically. It's supposed to
Factor.
undo what the other function did. It's supposed to be the opposite of what the first function was, yes? So I really hope it makes sense that if I switch the x, y, and I solve for y, I'm going to undo everything that was there. When I start to solve for y, I'm going to do all the opposite stuff. Are you guys at all with me? Okay, so on one level, it's not a hard thing to remember, but I still want you to know, why does it make sense we do this? Not just because it said so. Somebody's got to change a belt on something. I don't know what's going on. It did sound like a machine screaming somewhere. I don't know. So what letter am I trying to solve for?
Y.
Where are they all together?
No.
They're not all together. What do I do to get them all together? You can do two different things. Which side do you want all the y's to be on?
The left side.
Okay, so if you want them all to be over here, who's not there that should be there?
The two.
The 2y. And who is there that should not be there?
The 7.
So then I get 4yx minus 2y equals negative 3 minus 7x. Is that cool? 4yx minus 2y. This is gone. This is gone. Negative 3 minus 7x. So everybody see that? Now it still looks like there's 2 y's, but that's just an illusion. Right? Because what can I do with the y's now?
You take them out.
Or the 1y. I can take that 1y out, and I can see that there's only 1y. And then what's the last step to get y by itself?
Divide by 4x.
Divide by the crap I don't want. So this is f inverse. That's the opposite operation. Now, do you all agree this is a more complicated function? You all agree? The original function had freaking x's on the top and the bottom and all that shit. It was weird. So it's not immediately obvious that these are inverses of each other. This one and the original. It's not immediately obvious because there's a lot of shit going on, but they are. Just trust me. So that's how you do that problem. Which problem was it again?
12, 3.7.
3-7, number 12, yeah. So if there's ever more than one variable that you're trying to solve for, just get them all on one side and factor it out. There's not more than one variable. Just one that somebody gave to a lot of different parts. Yeah. Oh yeah. Yeah, I'll do you one better. I gotta move it all the way down here in a minute. You guys okay? You guys alright? Okay, that's better than I can take this. So in general,
And what is this one?
finding the inverse. Yeah. 3-7, number 12. Plus is the one you have to do plus for homework. Okay. All right. Anything else from homework stuff? Just to maybe propel some questions. Here's an announcement. So this Wednesday, we're going to have 3-5, 3-6, 3-7 quiz, and then on Thursday, the next day, We're gonna have a chapter 4 of this. Chapter 4 sounds like a lot, but it's 4142. You guys over with me? And I think I said this before, but trust me, you want more grades. If you don't know, now you do. You want more grades. If you're in a class and you haven't done a quiz and it's week 5, yeah, no. Give me something. Give me something graded now. You kind of with me? You want more grades. Okay. So when I don't give you quizzes, I always feel bad. I'm like, oh yeah, I forgot to give a quiz. Shit. What's happening next week? Yeah, dude, test 2. Holy shit! It's almost like this is a 6-unit class or something crazy. Yeah, so we got a bunch of quiz tests. We got. I think I'm giving 6 tests total in this class, which is crazy, but we only meet for an hour 20 minutes, so I've got to give you more smaller tests so they all fit. Okay. Anything else from homework stuff? Okay. All right. So let's see. There's no more questions. I believe last time we finished a couple of handouts. So let me see. Do I have? We did this one for sure. Graphing quadratic equations. And I think we did that one after we did the ones on the back of this one. So, does anyone need, oh shoot, do I have them? Oh, here we go, sweet. Does anyone need either of those two? Probably both. Hey. Everybody else good? Oh, sorry. So, I was about to say, here, we'll do an example because quite a few of you guys missed out on this. Don't forget the videos are up from the lectures. They're not meant to make the class become an online class. They can't. But they are there in case you missed a class or you want to augment your notes, whatever. You with me? So don't forget they're up there. They're not monetized. You shouldn't get any ads. Okay. But let's do an example real quick. We use 2 too much. Let's do 3x squared. Let's do negative 3x squared. Yeah. Minus, you do it, Jeff. Let's say, sure, 6x. Minus 2. I like it. So the instructions would say, put this into vertex form. Find y-intercept and graph. Well, find vertex y-intercept. That's why we're putting it into vertex form. Makes sense. All right. So some of you guys might not realize what vertex form is, and this came from transformations. So if the vertex started at 0, 0, and I shift right 3, up 5, now the vertex is at 3, 5. So if I put this in the form where we can see the transformations, I could just read out the vertex. That's the whole idea. It's very similar to solving for y for a line, and then I can see the slope and the y-intercept. It's a standard idea in mathematics. Do I actually have 2 sides to play with, though? Not really. This is just a function. What's the first thing I got to do if I want to complete the square? Because I want this to look like this. This is vertex form. I want it to look like this, because then I could just see the vertex. Because I could see the transformations, yes? What is the first thing I need to do then? Well, I'll take two things to start completing this guy's square. Make room. And what else can I do at the same time? So I'm going to push the -2 over here. Get out of here.
Factor out the -3.
Factor -3 out because completing the square requires a 1 here. Okay. I pushed that poor little -2 way over there. You'll be all right. Okay, now how do I complete this guy's square?
Cut the 2 in half.
Yeah. Cut 2 in half, you get 1 square, you get 1. So let me put that here. So I take 2, cut it in half, and then I square that. This is what I add here. Now what did I actually just do? I did not just add 1.
You
The same way this isn't really a 2. It's a -6.
added -3.
I didn't just add 1, I subtracted 3. So what do I have to do at the same time?
You add 3.
I have to add 3, so overall I did nothing. I can't change the problem, but I can reorganize it. Okay, I like it. Oh, so if I add 1 here, I really subtracted 3. I have to add 3 here. So now all of this is the same as this. Let's check. -3x squared, check. -6x, check. -3 minus 2 plus 3 is -2, check. So I still have the same problem. And of course, -2 plus 3 is?
1.
That's crazy. So can somebody tell me the vertex?
-1 and 1.
-1, 1. Can somebody tell me the y-intercept easily?
1.
0, 1.
Yes. 0. Well, no. If you plug a 0 in here, you got work to do. So where is it better to plug a 0 in? Here. And again, you have to remind yourself, I don't know if this is part of the problem, but it feels like this is part of the problem. This is the same as that. This is the same as that. This better be the same as that, or else you're losing a lot of points. These are the same. So if I want this guy's y-intercept, it's this guy's y-intercept. 0, -2. Okay, maybe.
So just from economics, the y-intercept on these kind of problems will always be the original y-intercept of the original equation.
And again, if you plug a 0 in, what's 1 squared?
1.
Times -3 is -3, plus 1 is?
-2.
Yeah, you'll still get -2 if you do the work. So it's not a question of, it's not like you can't use this. It's just, I'd rather not. I'd rather just be able to see it instead of do work. You with me? We're not being lazy. We're being efficient with our freaking time. Yes? So not a damn thing wrong to use this, but you see the most common mistake I'll get is somebody will just tell me it's this. But that's not what you get when you work it out. Okay, maybe. Screw you, Jeff. Did I lose anybody on any step? Yes.
The +3 can you explain?
Oh yeah. So we put this here, yes?
Yeah.
Is this really a 2 in the problem?
No.
What is it really?
So it's a
-3 times 2. So when I put a +1 there, I did not just add 1. What did I do?
-3.
I subtracted 3. So what I have to do at the same time, so overall I don't do anything, so I don't change the problem.
So do it to the same side.
The opposite.
I have to undo it.
And do it.
So if I subtracted 3, I better add 3.
Gotcha.
Yeah. Maybe. Okay. So really cool with that idea. If you have 8, and then you subtract 3 from it, and then you add 3 to that, what do you get? You don't have no work to do, yes? You have no work to do. If you have 8, subtract 3 from it, and you add 3 to it. What do you get? 8. What if you have 117, and you add 248, and then you subtract 248? 117. All right. So if I have something, and I subtract 3 from it, and I add 3 to it, it's the same. I haven't changed the problem. That's what I'm not allowed to do. Because then my answer is going to be wrong, because I'll be working with some other problem. Okay, maybe? It's a problem in morning classes. Some of us are tired and I'm trying to interpret what your face is telling me. And it maybe has nothing to do with the math, I don't know. Okay. So I highly recommend, if you were not here last time, you watched the damn video. We did several of these. It's a little weird when you have to work on the same side. It's definitely weird when there's a number out here. Whatever you put, you actually did this times that, and then you have to undo it. And then graphing this is not too bad. Is that true? Vertex is -1, 1. Y-intercept is 0, -2. Can anyone tell me where there's another point?
+1. To the right one.
Do it again, sorry.
To the right one.
1, 1.
Oh,
Oh, be careful, be careful. All right, where's the vertex? This is the vertex, yes? And it's opening how?
down.
Down. Now, please, whoever said that, I wasn't looking. You're fine, but you can see how that's a really simple mistake to make. If you're not careful, you might think that's the vertex, and there's another point by symmetry here. But that's not the vertex, this is. So where's the other point by symmetry? -2, -2, yes. So this is the mirror. Here's a point. There must be a point there. Yeehaw. Whoa. And remember how I check my work besides plugging in the graphing calculator? Plug in -2. So let's see. If I plug in -2 plus 1 is -1 squared is 1 times -3 is -3 plus 1 is -2. Yay! If I plug a -2 in, I should get a -2 out. So if you ever plot anything and you get another point, somehow you could plug that point in, make sure it's right. Okay, maybe. Yes, sir.
Do we ever need to plot more than 3 points when making a vertex graph?
No.
Okay, well, not a vertex graph.
Unless they ask you to, right? But if I just said graph this, you just need 3 points. 2 points is not enough, you need 3 points. And the easiest third point to get is the mirror image of the y-intercept. You could get the x-intercepts. Do you think the x-intercepts will be nice? How do I get the x-intercepts? How do I get the x-intercepts? Yes, set this equal to 0. And then what do I do from there? If I could, and I can't. You cannot factor that. So then what do I do? It's not surprising I can't factor it, because do you all agree that my x-intercepts are more than likely pretty gross? Look at them. Gaze upon them.
Minus b over 2a.
Say again?
Minus b over 2a.
That's finding the vertex. How do I solve this equation? What has the job to do this? Whose job is it? Do it again. Quadratic formula's job is to solve ax squared plus bx plus c equals 0. Because that's where it came from. Maybe. -b plus or minus. Right? The full quadratic. -b plus or minus square root b squared minus 4ac all over twice a blah blah blah. And what you'll get will be something that's negative point something and -1 point something. If you do it all and plug it in your calculator. Does everybody see that? You could estimate the x-intercepts. I don't trust my scale to be that great, but it's not bad. You guys okay with that? You guys okay with that? Because sometimes it will say find the intercepts. And that means y-intercept and x-intercepts. And how do you find the x-intercepts? You set it equal to 0, and you try to factor. If factoring doesn't work, quadratic formula.
Yeah, but if you do the shortcut, you'll get -6 over negative, or 6 positive 6 over -6, which would be -1. Which that was the. Yeah.
Yeah, totally.
But wouldn't that just be the? Oh,
And that's a great way to make sure that my vertex is right.
I know.
Yeah. And remember, this problem said put into vertex form.
Yeah.
So we had to do this. You can check your vertex by doing the shortcut, yes? the negative b over 2a. You can check your work.
Oh yeah, I thought that was just
Yeah.
another way of finding x2, because I was like, if it's negative 1.
No.
Yeah.
Defines the vertex.
Sure,
Okay. As a teacher, it's really troubling when I see faces that look like this, and nobody's saying anything. So I'm just gonna move on unless there's any questions. We could do another example. Okay, all right. I love this. Are you guys not used to, like, I don't know, not used to being able to just ask for whatever the shit you need? I'll shut it down if I need to keep going. Do you understand what I'm saying? You can always say, dude, hey, dude, can we do another example? And I'll do it, or I'll say, see me in the office, I gotta keep going. Either way, not a big deal. I'm not gonna, like, throw something at you. Okay. I did have a teacher that would throw things at people. That was exciting. So what if I have this here? What do you got, Jeff?
Blah, blah, blah. Blah, 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 blah.
Oh, this is gonna be interesting. Yes, okay, there we go. That's nice and gross. Ooh, make that a plus 21 at the end. Okay, that'll be a little bit better. So we got that, plus 21 at the end? Alright, so same instructions. Put the vertex form, find the vertex, find the y-intercept graph. First step is what? Yeah, I can do two things. I can take a 4 out of the first two, and I can make room. How do I complete this guy's square?
Divide negative 6 by 2.
Yeah, cut the middle dude in half, and then I take that number and I...
Square.
Alright, let me stop for a second, let everybody catch up. Which part of this is most immediately important?
The 9.
The 9, because what does that tell me to do?
Add it to that. And then
Add 9.
the opposite goes.
And what did I really just do?
And do it on the other side.
What did I really just do?
Added 36.
I added 36, so I better do what at the same time?
Subtract 36.
Subtract 36. Real quick, let me show you on the side here. Real quick. Can you guys make this have a 21 on the bottom?
Yes.
How do you do it?
Times 3.
If I just multiply this by 3, that would be a different fraction, correct? You agree? If I just left the top as 2, that is a different fraction. But if I also do it up here, so overall, what did I just multiply by?
1.
1. And that's why that damn thing works, of course, right? You guys got it with me? That's why that works, because I did something, but I did its opposite at the same time. So the fraction is the same, it just looks different. Yes? Yes?
That's 6 over 2 equals -3.
Do it, I'm sorry.
Is it 6 over negative, 6 over 2?
So negative 6 over 2, because the first step is take this guy and cut him in half. Yeah, sorry. So here, we added 36, so I have to subtract 36. The same thing as divided by 3, so I better multiply by 3. It's exactly the same idea. Nothing new at all, just we're not used to seeing it like that. How do you factor this dude?
X minus 3.
Yep. And now here I get,
Minus 15.
so what's the vertex?
3 and 15. 3 negative.
Good, 3, because it went right 3. Negative 15, because it go down 15. What's the y-intercept?
0 and 21.
Yeah. And if I want to graph this, what do I need to be careful about? It's a very broad question, I'm sorry. But I don't want my standard graph. I have to be careful about picking a good scale. Because the damn things are like 21. So if I'm, doing this freehand, I could use a scale of 3. Do you guys see how both of those have 3 going in easy, so it's nice? So if I use a scale of 3, 3, 6, 9, 12, 15, 18, 21, yay. And then this could be 1, 2, 3, 4, 5, 6. No, Jeff. It's the whole point, man. Okay. Now I need negatives. Negative 3, negative 6, negative 9, negative 12, negative 15. So my vertex is 3, negative 15. My y-intercept is 0, 21. So where is there a third point?
621.
Yes. So 3 over, 3 over. There's my reflection point. There's that weird guy that's staring at us. When we look in the mirror. Or girl. Okay. Yes.
How'd you get the lines?
Oh, how do I get the x-intercept? I said y to 0. How do you get the y-intercept? Make x 0. And so if they give it to me in this form, that kicks so much ass, I can just see the y-intercept
I see.
immediately. Okay, maybe. And again, if I put like a 0 in here, negative 3 squared is 9 times 4 is 36 minus 15 is 21. If you do it, you'll get the same answer. All right, is that better? Is that better? Sort of, okay. All right, it has to be because that's the last one I'm doing for now. Okay. Oh, I'm sorry. Did anyone finish? I'm taking it away too quickly, I think.
What's that last one?
This one? So this is 3 away from the mirror, so there's got to be a reflection 3 away on the other side. So it's 621. If I want to check it, if I plug a 6 in, I should get a 21 out.
I see.
Okay. Okay. So that pretty much finished up 5-1. Today I want to do 5-2, 5-3. See if we can do this. 5-2 is relatively quick. All 5-2 introduces is the idea of a power function. And all a power function is anything that can be written in this form. Let me not put in, and it'll be fine. Let me put a P there for power, where P is some real number. So then obviously, this is a power function. Wow. Right? What about, and of course this is a power function. What about this? Is that a power function?
Yeah.
Why is it a power function? Because I can write this as x to the,
1/2.
there you go. I can write it as x to a power. You guys see that? Just because it currently isn't written in that form doesn't mean it cannot be. So the same way, do you all agree with me that the decimal, this decimal is a fraction? Does anyone not agree with me? What fraction is this decimal? 0.3 repeating.
1/3.
1/3. So most of us know that. Just because I write it like this, does it make it not rational? Does it make it not a fraction? No, it doesn't. It's just written in a different way. So this is written in a different way, but it's still x to the 1/2 power. How about this? And I'm going to give it away by writing it down here. Is that a power function?
No.
Because it's not in this form. How many terms does this form have?
1.
1. How many variables does it have? 1. Well, p of them really, but you know. Okay, maybe. That's really all there is to power functions. Kind of silly. Kind of silly. That's all a power function is can it be written in the form constant times x to some power. How about 1 over x? I'm going to give it away. I'll put it up here. Why is that up here in this row? So this is because it's x to the 1/2. What's 1 over x?
X
X to the negative 1. Okay, good. So a fraction is any number that can be written in a ratio of whole numbers. A power function is any function that can be written as this. I like it. So if it's got more than one term, it's automatically not a power function. Now, that's all there is to 5.2. 5.3 says, okay, let me construct polynomials out of these power functions. Yes?
So only because there was that +2, it doesn't make it a power function?
It makes it not a power
Just
function.
because of that +2?
Yeah, this is not a power function because can I write this in this form?
No.
Can I somehow suck that 2 in? Nope. I like it. Even this is not a power function. That is not a power function because again, I can't write it like this.
What if it was just x squared?
Totally, just like x to the 5th.
Yeah, okay,
That's totally a power function.
okay.
Yeah. So another way to look at power functions is they can't have more terms. They can only have one term. A polynomial is by definition, it does two things. Multiple terms, that's what poly means. Multiple terms. So multiple terms. And each term is a power function where the power is a whole number. Okay, and this is kind of silly. You all know, when I say polynomial, does anyone have anything come to mind? Any specific kind of like algebraic thing? When I say polynomial. Anybody? Does anyone know, besides what I've written, what the shit that word means, polynomial? Sure. Totally, that's a polynomial. Ax squared plus bx plus c is a polynomial. X squared plus 2 is a polynomial. X minus 1 squared is a polynomial because it is a collection of multiple power functions where the power is a whole number. What's a whole number again?
8, that's not negative?
Not negative, integer that's not negative. So whole numbers are 0, 1, 2, 3, 4, 5. Okay, so you all know this. I know you know this. This is just a little more technical than you want to think about it. But here are some examples. 4x squared plus 7x. That's a polynomial. What about, and then of course x squared plus 2 and x minus 1 squared. Those are also polynomials. This is just factored. If I multiply it out, it'll be x squared minus 2x plus 1. What about this? What about, you ready? What about 11? Is that a polynomial? I put it there, but I could have gone temporarily insane. Is 11 a polynomial?
It's not multiple terms.
Oh, okay, I agree with you. I have to be careful. When I say multiple, okay, let me be a little more precise here. One or more terms. So like these are polynomials. These are polynomials, you with me? They're just specifically called monomials. Does anyone remember that? Like monocle? Like the one glass? But what's wrong with this? What's kind of wrong? Is that a polynomial? 11.
Are you saying it's because 11 to
No.
11 to 0? So?
What's got to be true about it's a power function where the power is a whole number. So every variable in it has to be raised to a whole number. What's wrong with 11 sort of? Does it have a variable part?
No.
You ready? You ready? You know me. You know me. I like to be contrary. It has a variable. It does. No?
0?
No. So, well, how many x's does it have? Tell me, how many x's does it have?
0.
So there you go. So that's another way to write the number 11. What is x to the 0? We know this. We talked about this. 1. So isn't 11? I love you guys so much. That's why It's whole numbers. Now, real quick, did you guys agree that x squared plus 2 is a polynomial? So then 2, therefore, must be valid. It is also a polynomial because it's every x value it's got is raised to a whole number. And x to the 0 is 1. So every constant you've ever seen in your life is automatically a polynomial. How we doing? I wouldn't freaking call it a polynomial if I'm doing 2 plus 7. Okay. I love you guys. What about this? What about, is this a polynomial? You can do it, Jeff. 3x to the 7th plus 2x minus x to the negative 1.
No.
Is that a polynomial?
No.
Looks like
Hmm?
yes.
Negative.
What's the two things? It could one or more terms, and every power has to be
A whole number.
a whole number. And what's the lowest whole number? The number that looks like a whole. 0. That's why I love the word whole number. It's freaking the first thing is the whole. So is that a polynomial? Why not?
Because of the negative one.
That's right. There's a negative power that's not a whole number. Nope. Try again, Jeff. Okay, what about this one? I think y'all are on to me. What about, you can do it, Jeff.
No.
Does it have one or more terms?
Yeah.
Does it have one or more terms?
Yes.
Yes. Is every power a whole number?
No.
Which power is not a whole number?
Pi.
I don't understand. Okay, we'll come back to this. We'll come back to this. Is this a polynomial?
Yes.
Yes. In fact, this is probably something that most people think of when I say polynomial. The brain normally goes to this kind of thing. Yes. What about this? We're coming back to 2, don't worry. We'll come back to 2. What about this? Yes! Because pi is just a stupid number. Pi is just a dumb number. Poor little dude, but he's just a dumb little number. He's just as valid as 3. Just as valid as the square root of 11. He's just really freaky, which is why we gave him a letter, so I don't have to write all that shit out. 3.1, 1. I don't want to write all that shit out. Let me just call it weird, and we'll truncate that to pi. Now look at number 2. Pi is not an issue. Yes, it's just a number. Pi is just a number. Who gives a shit? Every number is part of a polynomial, or could be, or is a polynomial themselves. So is what is number 2 good?
Yes.
No.
Look at all the powers. What power is this?
2.
And that, is that good?
Yes.
Yes. What power is this?
1.
Is that good?
Yes.
Yes. So what's the problem? Are you guys worried about the 1/5? Who gives the first shit about 1/5? Huh? Say again?
So you only look at the powers?
What was the rule? One or more terms. Every power is a whole number. Is that true? Yes. So just because there's a fraction somewhere doesn't automatically disqualify it. Now here's where you got to watch out. So I already gave it away. The answer here is going to be no. Sorry. You just make things so hard, Jeff. Okay. But tell me why the answer is no.
Because it's a power is a 1/5.
There's a power that's not a whole number. There we go. The power is fractional, that's not a whole number. No shot. All right, what about this?
No.
Yes.
Oh, wait. It was 2.
Yeah, what is 10/5?
2.
So is this a polynomial? Yes. Somebody just wrote it really weird, namely me, just to be all tricky. I'm sorry. Is everybody with me? 10/5 is just a fancy way to write 2, so is the power a whole number? Of course. Okay. Enough of that. So I know you all understand what the word polynomial, I'm pretty sure you do. You must have run into them before. And they're not really tricky. You only have to worry about two things. One or more terms, and the powers are all whole numbers. Yes? So, here. What about this one? One or more terms? Check. Are all the powers whole numbers?
Yes.
Yes. So it doesn't matter if there's more than one variable, that's fine. It's just all the powers have to be whole numbers, and there must be one or more terms.
Is that if you graph that, would it be 3D? If there was an f of x that equals it? Yeah.
Yeah, inherently, because it would be y equals this, and then you have three variables, so you have three axes. Yeah. Is that cool? Or is that understood? That specifically would be highly tricky. It would probably be like a three-dimensional spaghetti thing, which would be really neat. Okay. We're not going to graph this, all right? Don't worry, but you are going to have to be able to discuss it. Okay. So, all right. Now, to get a little bit trippier. Let me see how to introduce this. Okay. If I have this here, can you guys tell me the x-intercepts of this? How would you do that? How do you find the x-intercepts?
Set y equals 0?
Sure. And then what? Sure. How do I do that?
Factor out x.
There we go. A factoring, right? You with me? Quadratic formula's job, but only if factoring doesn't work. Can I factor this?
Yeah, take out an x.
Everybody always forgets poor little GCF. GCF is always there. And of course, what are my two answers? X is 0. X is 2. Now, we all know what this looks like. What shape is this going to take?
Parabola.
Parabola. Is it going to look like me? Oh, you mean you. Okay. It's going to take on the shape of a parabola. Let me ask you a really strange question. What is it going to do at its intercepts, at its x-intercepts? What's it going to do? Is it going to go through the x-axis, or is it going to turn at the x-axis?
Gonna go through.
Yeah, this is a weird question you never thought about. So it's got an intercept at 0, intercept at 2. Where's the vertex, by the way? Do you have to do much work here? Here's an intercept here. There's an intercept here. For the vertex, x has to be 1. Is that cool? Because it's right in the middle. The line's got to be, the axis of symmetry has to be here. How do you figure out the rest of the vertex point?
Plug in 1.
Holy shit. 1 minus 2 is... Yeah. So then my parabola looks like this. And what's it do at its x-intercepts? It goes through, yes? All right, I'm going to start to lay some groundwork here. This is always a trippy idea to get into. And you never really thought, yes, good.
Did you get the vertex?
Oh. If I know that a parabola goes through a point here and a point there, where's the axis of symmetry have to be? In the middle, which means that's where the vertex is. Because what's the axis of symmetry do? Goes through the vertex. So therefore, I knew the x value of the vertex is 1. And if I know the x value, I plug it in to get the y value. Good. We really just use negative b over 2a, but more visually instead of computationally. Here, let's double check. What's b? What's b up here?
Negative 2.
Negative 2 is the one in the middle, right? And what's a?
1.
1. So negative b is negative, negative 2 is 2 divided by 2a. 2 divided by 2 is 1. So if you use negative b over 2a, you'll get it also. But I didn't need to. I knew the intercepts. I can see where the vertex must be. Let me stop for a minute.
If we make a test questions and maybe don't show the work for that.
Do it again, sorry.
I said, like if it's like on the test and individually, do we still have to show the work that's like plugging in negative?
If this was on a test and you got this way, I would like to see like something, something that tells me that's what you thought. Yeah, especially if you could be using your calculator on that part, because
Oh,
I never know if people are just like, oh, I know it, didn't know. Okay, sorry. So, let me ask this really weird question again. At the intercepts, did it go through them or did it turn at them? It obviously went through. Do you see what I mean? It went through them. Yes? And you're all like, dude, keep going. I don't know what the hell you're talking about. What about this? What's the difference here?
That's to the power of 2.
In vertex form.
Yeah, it's already kind of in vertex form. It's already been kind of collected. Somebody maybe already did the completing the square. Whatever you want to say. What's the x-intercepts? There have to be 2 of them. But what are they both? Well, look at it this way. What's the only x-intercept? What makes the output 0? 1. But how many times does it show up?
2.
Twice. So let me make sure you guys are really, really with me. Do you agree that these are both parabolas, but they fundamentally look very different from each other? Yes? So this one, the x-intercept is 1, 0, and it shows up twice. Yes? Because this is x minus 1, x minus 1. So how often does 1 work? Once, twice. The technical name for that is it has a multiplicity of 2. The root of 1, I might not have used that word before. Another way to say x-intercept is root. And it literally is because if you look at this as the ground, those are where the roots start. They were plants. So you'll see the x-intercept referenced as the root. Has anyone ever heard that before? Maybe. Okay. I love you guys so much. Okay. So the technical name for this phrase is it's got multiplicity 2. Multiplicity blank just means that's how often that root showed up. If I look back at the one we did up here, what was the multiplicity of each of these roots? How often did I get 0? How often did I get 2? It's a weird question, but
1.
each one showed up how many times? Once. So their multiplicity was 1. So tell me, what does a line do? Does it go through the x-axis or does it turn? If it turned, would it be a straight line anymore?
No.
So let's try this again. What's a line do? Does it go through or turn?
Through.
Through. And what's a parabola do? Turns. Okay, now, here's where you really got to be careful. I know this is a parabola, but each of its intercepts are lines. Isn't y equals x a line? Isn't y equals x minus 2 a line? That's why when I'm really close to 0, it's acting like this line. It goes through. When I'm really close to 2, it's acting like a line that goes through. Maybe? No? Not at all. No, I don't like that. Don't you tell me no, sure. Sure, just
Absolutely.
say it. Tell me what to do, make you happy, so I can pass the class, Joe. Stop doing what you're doing right now. I'm sorry, okay. Stay with me. This is such a cool idea, and I understand it's a real trip, because we're doing things we've done before, and it feels like I'm making them harder, but we're going to look at much more disgusting functions, and I'm trying to lay some groundwork so we can look at them correctly. So far, we haven't graphed anything too freaky. But you know there are functions that look like Loch Ness Monster kind of thing when you graph it. You have a lot of twisty shit. And I want to know a quick way to tell is what's it going to do? Is it going to hit its x-intercept and go through, or is it going to hit the x-intercept and turn? And it's a very straightforward thing to consider. If where a root came from has an odd multiplicity, it's going to go through. Through, through. If where it comes from has an even multiplicity, it's going to do what parabolas do. It's going to turn. Let's graph this Isn't this just x squared, but it's been moved over 1? You guys agree?
Mhm.
So if I look at it like a transformation, here's x squared, and it's just been moved over 1. Yes? It opens how? Up. This is not enough to graph this, is it? If I just put a U shape, do you know you got the how wide it is correct? No. So what else do I need? Don't I need another point? What's the y-intercept? -1 squared is? Yeah, so when you plug a 0 in, you get 1. Is that cool? So here's a y-intercept, so here's another point. So then it looks like this. What did it do at 1? Did it go through at 1 or did it turn at 1?
Sure.
Go through.
Did it go through
Oh, sorry.
or did it turn?
Turn.
Yeah, I'm sorry. When I said at 1, I meant the x value 1. Okay. I really want this to make just fundamental sense. This is so cool. This isn't about the whole graph. This is what is happening at the root. So both of these are parabolas. But how does this work at the root? Isn't the root squared? So at the root, it should look like a parabola. Up here, what was true about each root? First power, it should look like lines. In fact, let me try to go one step further with this. If I'm really close to 0, it should look like this line. Notice though it's going down, yes? But if I'm really close to 0, can anyone tell me anything about the number that comes out of this if I'm really close to 0? Negative, yes? So when I'm really close to 0, this should look like -2x. And sure enough, that looks like a line, -2. It looks like it's -2x going down through the intercept. Over here, if I'm really close to 2, this is close to 2, it should look like 2x. And it does. So, we've learned that if I factor what I'm given, if I factor the polynomial I'm given, I can see how often each root shows up and I know what's happening at that root. Let me try to push this one step further. Oh, you got time. Look at me go. Okay. Now, first thing I want to ask you guys, without multiplying this out, dear God, you never have to multiply this out. In fact, normally we're going to have to do the factoring. But this is already factored for us. Thank you. Without multiplying this out, what would the highest power be if you did?
3.
Third power. Does anyone know the basic shape of a cubic? Yes, I love it. I love when people do the like. So you got x cubed. I'm not going to suddenly try to do stay alive. You guys with me? So I know it's going to look like this, at least on the outsides. Okay, so this is where things get tricky. A basic cube looks like this, yes?
Wait, do you like a cubic at the power of 2, the other one we're going to assume that's the power of 1, and we just put 2 plus 1 is 3? What do you know it's cubed?
This would give us x squared times x is x cubed. So if I did FOIL this out, what's the highest power I would get? Third power. And here's where things get, now listen, this is if I had x cubed. If I had x cubed plus other shit, like 2x squared minus 7, if I have other shit, if I have other pieces, let me see, I need to talk about this by itself. We'll come back to this. If I had, for example, if I had this is still a cubic, yes? It's just not simple. It's not like x cubed, it's not simple. When x is really big, which term dominates?
Highest power.
Yes, the highest power dominates, yes. So when x is a billion squared is pretty big, and then I double, that's pretty big. But this is freaking a billion cubed, which is a billion times bigger than a billion squared. Are you guys? So when x gets really big, these almost don't matter. When x is really small, now these terms matter more than this. That's why when I graph something like this, it looks like a cubic on the outsides. It looks like a cubic on the outsides. Because when x gets really big, this is the most important term. But in the middle, it could wobble. Because in the middle, I'm close to 0, and then these terms matter more. This is the idea of end behavior. What's it doing at the ends? And then the wobble shit we'll figure out when we plot the intercepts. So this one's got a degree. What's the degree of this one? Like x cubed. So on the outsides, it should do this. It should go up over here, down over there. If it was x to the 4th, on the outsides, it should look like this. Odd overall degree, even overall degree. And maybe.
When you get to like, say x to the 5th, is there
That
going
is
to
just
be
cubic.
more wobbles in the middle?
Beautiful. When you have x squared, how many terms can you have? You can't have more than one term, correct? So when you have an x cubed, how many terms do you think I could have? If I can have 1 when I have x squared, how many can I have when I have x cubed? 2, 4, 3, 5. I could have 4 terms. I can go 1, 2, 3, 4, yes? And then that would be the overall graph. Yeah, I like it. So, let's take a step back. Now I know what this thing is doing on the outsides. If I look at the intercepts, I can see what it's doing in the middle. What are the x-intercepts? 2, 0, and can you guys just tell me what their multiplicities are?
2.
Yeah, how often did 2, 0 show up? Twice. And how about negative 4, 0? Once. Okay, good. So, I used to say, and I think I just did earlier, does it go through or does it turn? Those two words, if you write like I do, they look the same. So I call it, does it go through or does it bounce? Does it go through or does it bounce? What does it do here? Does it go through or bounce? Multiplicity 2. So what's it look like at that point? It looks like a parabola. It looks like an x squared, yes? I need you guys with me. If you showed it twice, it came from something with a power of 2. Power of 2 looks like this. So what's it going to do is at 2, 0, it's going to bounce. It's going to turn. So if you want to call it turn, you can. So it's going to turn or bounce. See the way I write turn?
Oh,
If you squint, doesn't it look like it's through?
wait, so the multiplicity just tells you what direction the line is going on the graph?
Yes. This is related to the power, and a parabola, Jeff, turns. What's it going to do at negative 4, 0?
Goes through.
It's going to go through. See how far away those look the same? That's more just about the way I write things. Okay. Let's see what we can do here. So I know it has an x-intercept at 2 and negative 4. So 2 and negative 4 has intercepts. Can somebody tell me the y-intercept really quickly? How do you get the y-intercept? You make... What's that?
0, 2,
Negative 2 squared is
4,
times 4 is
16.
all right. So this the y-intercept is 0, 16. So let me do this scale by 2s. 2, 4, 6, 8, 10. That's probably a bad choice. Let's do 4s. 4, 8, 12, 16. There we go. Okay, so I got my x-intercepts. Got my y-intercept so I can figure out what kind of scale I want. Okay. I love you guys so much. How many problems have we done like this? We're not done with the first one. We did 2 very basic ones. This is our first real problem. Yes?
Just like the multiplicity, so the number of that determines what exactly?
I'll show you. Here, we got to do this, and I'll show you. So as I come, so I know I start down here. I know I start down here. I know I start down here. What did I say is going to happen at -4? Am I going to turn, or am I going to go through? Am I going to bounce at it, or am I going to go through? I'm going to go through. So I'm going to go through this one. Then I got to get here, yes? Later I'll show you how to make this a little better. What am I going to do when I get to this thing? Yes, I'm going to bounce or turn. There. This is like a standard cubic.
For the y-intercept, we always go through it, right? For the
Yes. Yeah. If you try to balance at the y-intercept, you don't have a function because now you don't pass the vertical line test. Yes.
How did you get the y-intercept?
Oh, just plug the 0 in for x. That's how you always get it. Unfortunately for us, this wasn't given to me in a form where I could just see the y-intercept. I had to actually work it out. But I'd much rather have it factored anyway. So I'm cool with that.
Can you give us one more example?
Do it again?
Can you give us one more example?
No, that's not what I. Yes, all right. This is only one example we've done so far. One thing we could do. Does anyone have any suggestion? Does anyone see what part of this graph? All right, before I get there, I'm sorry. Is everybody semi-cool with this? We have barely done any of this yet. But how did I know it didn't turn here and it did turn there? Was the multiplicities. Did it come from a second degree? Yes, so it should act like a parabola here. Did it come from an odd degree? This one did. Okay, so it should go through like a line or a cube. It should go through its intercept. Okay. Is there any part of this graph that's a little ill-defined? Like, if I just had a little more information, it could have graphed it better. And I sort of did. I couldn't stop myself. Do you guys see how I went up? I wouldn't blame you if you just went straight over from this, but doesn't that, I hope to somebody that feels wrong. Don't you agree that I should have information about an output in here? Mm-hmm. If I would have done one more thing, I could have made my graph look a little bit better. What's a good point to plug in that would tell me about how high it gets here? -2. -2, kick ass. So if I plug a -2 in, just to remind you guys, h of x was x minus 2 squared times x plus 4. If I plug a -2 in, that's -2 minus 2 is -4 squared times -2 plus 4 is 2. And that would be 32. So if I would have done this, which is fine I didn't, because there's a lot of little parts to this. If I would have done that, I would have known to make my scale better, because I should have gotten up to, at -2, I should have gotten up to 32. Then it would have felt more natural as I do this. That would have had a better shape to it. Yes, sir?
Is there a better trick to finding the local maximum?
That is calculus's job.
Oh, okay.
If it's a parabola, we can do -b over 2a. The minute it's higher than degree 2, we don't know shit. Can somebody tell me this though? There's one thing we know. Do you all agree with me that this is going up? Is this a positive slope? Yes?
Yeah.
What happens now? Negative slope. So what's true right there? Positive slope, negative slope. So what's true right there?
Neither positive nor negative.
So what kind of slope?
Vertex.
What number is neither positive nor negative?
0.
0. So it's got a 0 slope here, yes? So just to give you a little preview, in calculus, the first thing you learn is how do I find the slope for something that's not straight? So do y'all agree this slope here is changing all the time? Is it really big positive? Then it's less positive, and then it's 0, and then it's more negative, more negative, more negative, yes? And I know the slope is 0 here, so I'm not going to go down that road too far because you'll do that when you get to calculus. But just so you know, there is a way to find the maxes and mins, and that is a huge part of calculus. The minute it's more than a parabola, we're screwed. We don't know. We just have to kind of guess. So, I think your real question is, how do I know it doesn't go higher than 32? We don't. We just take a guess. Okay. Let's do note. What time we got? Okay. Ooh, that's gonna be nice and gross. I love it. What is the overall degree now? If I were to FOIL this, dear God, don't FOIL this shit out. You see how long that would take?
To the 7.
7th power, yes? 7th power is an odd power. Does it look like this or does it look like that at the ends? It should look like this at the ends, yes? So I know what's called my end behavior. Forever now it's going to be called EB. My end behavior goes like x to the 7th, and that looks like this. It's just the middle does some wobbly shit that we're going to figure out. The middle does some wobbly shit. Now what are my roots?
3 and 1.
So 3, 0,
Negative 1.
-1, 0. What's the multiplicities at each root?
2.
So this is twice, 5 times. This is even, this is odd. So what's it going to do? What's the behavior at the roots?
Goes through. Oh, I'm sorry, that bounces.
This one is going to bounce, or churn, whatever you want to call it. And this one is going to
Go through.
go through. Maybe if I write the whole word out, it'd be better. Let me stop for a minute. This is trippy. This is the most analytical work we've ever done with graphing. We're graphing some of the best shit in the world. Polynomials kick so much ass. They are nice. We call them well-behaved. We're gonna have functions that do all kinds of weird shit. They go wow, 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 and they go whip, wow, and they do all the polynomials are nice. But they got a lot going on anyway. What's the y-intercept?
10?
Nope. Negative 3 squared is
9?
times 1 to the 5th.
1.
1. So 9 times 1.
Oh,
Yeah, this is times, yes? Be really careful. Okay. Now, here's what I normally do. The x-axis is determined by my intercepts, what kind of scale I want to use. And both of my intercepts are nice numbers, 3, -1. So I'm going to use my x-axis is going to be by 1s. And I have an intercept at 3, 0 and an intercept at -1, 0. I'm going to get my y-intercept is up here. Is there another point I could plug in? I'm somewhere here. Once I get the scale for this, I'm going to put my y-intercept. But is there another point I might want to get?
2.
Yeah, okay, 2. So let's figure out what is f of 2. Let's see, what's f of 2? 2 minus 3 is -1 squared is 1. 2 plus 1 is 3 to the 5th. Oh shit. 3 to the 5th is 243. Okay, so you guys are all with me. 243. You with me? Alright, let's do 1 instead. Is that alright? You guys see that? This will be 243. Do I want to make a scale that goes up? Not really. I just know it's going to go really high. What's f of 1? That would be -2 squared is 4 times 2 to the 5th. 2 to the 5th is something, 32 times, what did I just say? 4. That's still 100 and something, which is more doable actually. So this will be, what did I just say? 32 times 4 is 100 and something. Yes.
Where are you getting the 4 from?
Oh, if I plug a 1 in, what's 1 minus 3?
Oh, okay.
So that'll be 4 times 32 is 128. Yes, that makes sense. So let me see. Let me make the scale like this. 20, 40, 60, 80, 100, 120, 140. All right, my y-intercept is 0, 9. That's way down here. At 1, it's at 128. And then it goes even higher than that. Okay. Let me make these a little bigger. All right, what's my end behavior? I start down here. What am I going to do at this intercept? Going to go through. So I start down here. I go through this guy. Oh boy. This scale is horrendous. I think I actually have to go like this. This is a horrible thing. Oh yeah, what is it happening there? Okay, that'll be fine. It's got to do this kind of thing. Then it goes up higher. What am I going to do at this one? I'm going to bounce here. So I really should have come at it a little bit better, but that's all right. Holy shit. All right, now that was a gross one because I made the powers really big. That was really gross. I agree. So I had to come through. I had to get through this. It went up higher. We know it goes up higher. And then I had to come back down, bounce. So let's see what it looks like in the calculator here. I got just a few more minutes. If I put in here x minus 3 squared.
You're not typing anything.
Oh yeah, I love this calculator. X minus 3 squared times x plus 1 to the 5th power. Now, if I just hit graph, it's not going to work really well. I'm going to make my scale the same way I did here. I'm going to go -4 to 4, and then I'm going to go, so I'm going to go window, I'm going to go -4 to 4, and then I'm going to go -80 to 140. So I'm going to try to mimic my scale I have here. Let's see what this thing looks like. All right, not too bad. That's pretty close.
Mm-hmm.
This one should just kind of like go like that a little bit, but yeah. So real quick, I'd rather see this, maybe not this, you could use pencil of course, you can erase shit, but I'd rather see this and not that. The most telltale sign that somebody just copied from their calculator is they'll do this weird shit here. Do you see that? That's like, oh, I didn't go up high. So don't do that shit. Yes? You guys kind of with me? So your graph should not be perfect. It should just capture what you found through your work. So if your work is wrong, but your graph is right, you lose a decent number of points. If your work is wrong and your graph is wrong, but it shows your work correctly, you will not lose as many points. Because one of the main things when testing go on is, can you take what you did and put it into graph form? Maybe. All right. I have put you through enough. I will see you tomorrow. Don't forget Wednesday and Thursday are quizzes. I'll put that back up here in case you missed it earlier. Where'd I put it? There it is.
I was